Okay, we're given a problem where we have something that's rotating. Might be this strap rotating about some axis. It is rotating at 5 revolutions per second, about maybe, that was maybe about 3, somewhat faster than that. And then it slows down to 2 revolutions per second, and I ask it what rate its rotation is changing. Also, what's its average rate of rotation, the average rate at which it's rotating. Okay, so I'm going to put a little terminology in this, but if it's, you can think about this now, if it's rotating at 5 revolutions per second, a little later it's rotating at 2 revolutions per second, on the average, how fast is it rotating? And then if it's rotating at 5 revolutions per second and a little later at 2 revolutions per second again, what's the change in the rate of rotation? Okay, now the rate of rotation we're going to talk about as an angular velocity. Now when people started doing this, they just started treating this as 2 velocities. They averaged the 2 velocities. They took the difference. At least the majority of people did. So this is treated just like a velocity. Some people even used v for the velocity, and that was fine. That was pretty much what I would have hoped for, I guess. Now, I'm going to say, after letting people work on this for a couple minutes, people quickly determined that the average rate of rotation was the average of the 5 and the 2 revolutions per second, or 3.5 revolutions per second, and the change in the rate of rotation was from 5 revolutions per second to 2 revolutions per second. Subtracting the earlier from the later, that's a change of -3 revolutions per second. So, and some people even went so far as to, okay, so the rate of change, we're going to divide the change by the time interval and get -0.25 revolutions per second squared. Not everybody got to that point, but most people got to this point here. But people were using V, like V naught and VF, very natural thing to do because you know how to think about uniformly accelerated motion. But this is rotational motion. And there are important differences between motion along a line and rotation. In the first place, in rotation, you never go anywhere except around this circle. And there are more significant differences that we'll see in a little while. But right now, we just want to know how to deal with this. Now, because there are differences, we don't use V for the velocity. We call the velocity, the rotational velocity, we call it angular velocity. Okay, angular velocity we designate by omega. That's an omega. It's not a W, it's an omega, O-M-E-G-A. You don't type it as W, you type out O-M-E-G-A, or if you want to go into your word processor and go through way too much trouble to change a font and then change it back, you can actually, you have a character, you have an omega character, just go to the symbol font. But I don't recommend you do that. It's much quicker to type omega. Short word, fairly easy to type, lays under your hand very nicely. Okay. Okay, well, now, what are we given here? We're given an initial and a final angular velocity. Now, as I say, people treated this as an initial and final velocity, and that was perfectly exactly what I would have hoped for, as I say. So we're given that, and we're given delta t, given omega naught, omega f, delta t. So here's our situation. We're given omega naught, omega f, and delta t. That's just like being given v naught, vf, and delta t, except that now it's angular velocity instead of linear velocity. The definition of angular velocity is the rate of change of angular position, and angular acceleration is the rate of change of angular velocity. Completely analogous to the definitions of average velocity here and average acceleration in the case of velocities. The reasoning is identical. The quantities are a little different, and we'll see again what some of the differences are, other than the obvious ones, but the reasoning is completely identical. So, if we know omega naught and omega f, the question I ask is, what can you determine? You'll say, well, okay, you can add them, divide by 2, and get omega average. Exactly. Or you could subtract omega naught from omega f, the earlier from the later, and get the change in omega. And having done that, you could take the average omega, which is the average number of revolutions per second and multiply it by delta t and get an angular displacement, which we designate by delta theta. Okay, now we might want to stop and think about why we use theta. Well, theta is a perfectly good, revolution is a perfectly good measure of angle. Okay, right here. Here's a strap. I rotated up to here. How many revolutions was that? Well, that was a quarter of a revolution. There's a quarter, there's another quarter, there's another quarter, and there's another quarter. We're back where we started from. So you could also say that's 90 degrees. 90 degrees is a perfectly good measure of angle, but a quarter of a revolution is an equally good measure of angle. Now, one revolution would correspond to 360 degrees, but revolutions were around before anybody invented degrees. So revolution is your most natural, in many ways, measure of angle. And we'll see the radian shortly, which is also a very natural measure of angle. Degrees are kind of artificial, but 360 was a good choice. You could divide 360 by lots of numbers. For example, here we go. Here's here's a 90-degree rotation, right? Now here's half of a 90-degree rotation. Now let's go back. Why is this a 90-degree rotation? Because they're 360 degrees around the circle, and this is a quarter of a revolution. So the revolution's more basic. It's a quarter of a revolution, and then that turns out to be a quarter of 360 degrees or 90 degrees. Okay? Now, what's this? This is half of a 90 degree. Well, that's half of a quarter of a revolution. That's an eighth of a revolution, and 8 into 360 gives you 45, so it's 45 degrees. Okay? What part of a revolution is 30 degrees? Okay, that's about 30 degrees, isn't it? That's about a third. 1, 2, 3 of those makes 90 degrees. So that should be about 30 degrees. What fraction is that of a complete revolution? Well, you figure that out. 30 goes into 360 12 times. It's 1/12 of a revolution. So degrees, revolutions, they are both measures of angle, and so is the radian that we're going to introduce shortly. But right now you know two measures, and you're actually very familiar with two measures of angle, revolutions and degrees. And you've worked a lot more with degrees than you have with revolutions. And as I say, degrees are a good measure, but our preferred measure is actually going to be radians, but we'll see that. Right now you should understand, you can measure angles in degrees, you can measure them in revolutions. So 5 revolutions per second, well, 5 revolutions is an angle. It's equivalent to 5 times 360 degrees, right? Okay, and 5 times 360 is 1800, so that'd be 1800 degrees. And 5 revolutions per second is 1800 degrees per second. You don't have to completely understand that right now. But like I said, it kind of passed. I haven't written it down. But that justifies, all that justifies using delta theta as your angular displacement. Okay, this delta theta is going to be in revolutions. Our average angular velocity is 3.5 revolutions per second. Time interval is 12 seconds. So if we multiply 3.5 revolutions by 12 seconds, we get the number of revolutions, and we get 42 revolutions. We're going to say delta theta, the change in angular position, is equal to omega average times delta t, and in this case, delta theta is 42 revolutions. Okay, now what about delta omega? It's -3 revolutions per second. The rate of change of omega is what? The rate of change of omega with respect to t, by definition, has to be delta omega over delta t, which is your -3 revolutions per second divided by 12 seconds, or your -0.25 revolutions per second squared. Now, if instead of 5 revolutions per second and 2 revolutions per second, this had been 5 meters per second and 2 meters per second, we would have reasoned it out over here. 5 meters per second, 2 meters per second, averages 3.5 meters per second, multiplied by 12 seconds, you get 42 meters instead of 42 revolutions. Nothing wrong with that. And your delta V would be -3 meters per second, and you would divide that by your delta T, and you would get -0.25 meters per second squared. There's a complete correspondence between the way you reason out velocity and the way you reason out angular velocity. Now this angular rate of change of angular velocity we also call angular acceleration, by analogy with the acceleration here. And we use the Greek letter alpha. Okay? So we have alpha, omega, the beginning and end of the Greek alphabet, the alpha and the omega, and delta theta. Okay. Okay, well that's your scheme for reasoning out angular motion. Now we'll go on with another problem in the next video clip.